Chapter 10 is all about gases. So, number 4. Imagine that the reaction between 2 moles of carbon monoxide and 1 mole of oxygen makes 2 moles of carbon dioxide. Occurs in a container that has a piston that moves to maintain a constant pressure when the reaction is at a constant temperature. All right, so what happens to the volume of the container as a result of the reaction? Explain. All right, so this is a constant temperature, constant pressure situation. According to Avogadro's law, in that situation, I can treat liters of gas like moles of gas. So I can talk about 2 liters of carbon monoxide reacting with 1 liter of oxygen to make 2 liters of CO2. So if we're looking at it that way, this is a volume reducing reaction. I'm losing liters of gas during this reaction. 3 liters are going in and only 2 liters are going out. So ready, set, go, we react, the volume decreases. All right, resetting. If the piston is not allowed to move, what happens to the pressure as a result of the reaction? I guess in a way it's kind of looking like this, like Dalton's law of partial pressures. As long as the volume is constant, the temperature is constant, I can treat moles of gas like pressures of gas. I can talk about 2 atmospheres of carbon monoxide reacting with 1 atmosphere of oxygen to make 2 atmospheres of CO2. So looking at it that way, this is a pressure reducing reaction. Ready, set, go. We lose amounts of gas in the container, so I have less collisions with the wall, and the pressure decreases. Number 9, consider the following graph. If curve A and B refer to 2 different gases, okay, helium and oxygen at the same temperature, which is which? Explain. Okay, so they're at the same temperature, so that means they have the same average kinetic energy. But because the one gas is lighter, it's going to move faster. All right, so you're going to have more particles moving at a high speed than you will the heavier moving gas at the same temperature. So kinetic energy, right? Mass times speed squared. So if you're a massive gas like more massive gas like oxygen, more of the particles will be moving at a slower speed, and with the lighter gas, you'll be more particles will be moving at the higher speed. All right, B. If A and B refer to the same gas at 2 different temperatures, which is the higher temperature? All right, so in this situation, if they're the same gas, higher temperature, higher average kinetic energy, that means more of the molecules are moving at higher speed. So the higher temperature gas, you'd have more particles moving at the higher speeds than you would at the lower temperature. All right, redraw the graph, but put in vertical lines to indicate the approximate positions of the most probable speeds and the root mean square speeds for the curve. So at higher temperature, I'm sorry, this was the last one, right? At higher temperature, the more particles were moving at higher speeds. All right, so this one, most probable speed is the top of the hump. So the most particles, that's what this graph refers to, most particles are moving at high speeds at the top of the hump. So looking at this particular speed, I have the most particles moving at a most probable speed for A at the one line. And if we're talking about root mean square speed, that's an average. And because there's more opportunity to move fast, the root mean squared speed doesn't match up with the most probable speed. It's a little bit shifted forward because there's more opportunities to have gases moving at higher speeds. I mean, we have a set speed limit for molecules moving at slow speeds, right? That's at 0 Kelvin. So way more opportunity for moving at high speeds than low speeds. Number 11. A thin glass tube 1 meter long is filled with argon gas at 1 atmosphere and is stoppered with cotton plugs. Okay. Hydrogen chloride gas is introduced to one end of the tube, and simultaneously ammonia gas is introduced to the other tube. When the two gases diffuse through the cotton plugs down the tube and meet, a white ring appears due to the formation of ammonium chloride solid. Okay, so the argon gas is the medium through which these gases are going to diffuse. All right, so at which location, A, B, or C, do we expect the ring to form? Explain. Well, I expect it to form at A. And the reason for that is ammonia is lighter gas. It's going to move quicker down the tube than hydrogen chloride gas is. So they'll meet at around spot A, and that's where the ring will form. And it's all about diffusion, right? Lighter gases diffuse quicker than heavier gases. Rate of ammonia is versus the rate of hydrogen chloride gas is inversely proportional to the molar masses. That's what the capital MM stands for. Square root, inversely proportional to the square root of the molar masses of the gases. So this is a way of calculating how much faster, right? Plug in the molar masses, how much faster ammonia is going to diffuse than hydrogen chloride gas. Number 22, perform the following conversions. A, we want you to convert from atmospheres to torr. Torr is in honor of Torricelli. For every 1 atmosphere, there's 760 torr. So atmosphere is in the denominator, torr up in the numerator. That's what I'm converting to. So we have less than an atmosphere, so we have less than 760 torr. 765 millimeters of mercury. Well, millimeters of mercury and torr mean the same thing. 760 millimeters of mercury for every atmosphere. Again, I have less than an atmosphere here. Atmosphere goes up in the numerator. What I want to get rid of, what I'm canceling, goes in the denominator. I want to go from pascals to atmospheres. I'd go to kilopascals first, right? There's 1,000 pascals for every kilopascal, and then there's 101.3 kilopascals for every atmosphere. I just think it's easier to remember 101.3 kilopascals than 10,000 pascals. Everything cancels except for atmospheres. Okay, these are our units we're dealing with, right? Pascals, atmospheres, and millimeters of mercury. This is called a manometer. It was a tool used for measuring gas pressure. If atmospheric pressure is 0.99 atmospheres, what is the pressure in the enclosed end of each of the following 3 cases? Well, we only did 2 of them. Depicted in the drawing. Assume that the gray liquid is mercury. All right, so the way this thing works, all right, so I've got well, for both of them, the atmospheric pressure is 0.995 atmospheres. So I want to get it in millimeters of mercury in order to use this mercury column. And I want to get the mercury column in millimeters of mercury, right? 10 millimeters for every centimeter. So anyway, this is the pressure in millimeters of mercury. The way this manometer works is the open end is open to atmosphere, right? So atmosphere is pushing down through the opening, and the gas inside the tube is pushing out of the container the other way. So in the situation where the gas pressure inside the bulb is less than outside, then in essence atmosphere pressure is winning, right? It's driving the mercury column up into the gas pressure, or the gas that you're measuring's area. So the extra distance that the atmospheric pressure is pushing up into the manometer has got to be subtracted from atmospheric pressure to get the lesser pressure inside the manometer. So you take the height of the mercury column. The height of the mercury column is 520 millimeters, right? So just multiply by 10, right, to convert centimeters to millimeters. And then you'd subtract that. You subtract the extra distance that you're being pushed up into the manometer from the atmospheric pressure, to get the lesser pressured gas inside the manometer. All right, in situation 2, the gas pressure is greater than atmospheric pressure, right? We're pushing up into atmospheric pressure zone. Oh, they wanted in atmospheres, right? So convert from millimeters of mercury to atmospheres, and there we go. We have less than an atmospheric pressure inside the manometer. So with situation 2, the pressure inside the manometer is greater than atmospheric pressure, so it's pushing the column up into atmospheric pressure zone. So the extra distance that the mercury is traveling is added to atmospheric pressure to get the greater pressure inside the manometer. The height of the column is 67 centimeters, so that's 760 millimeters. Add that to the atmospheric pressure, and that would be the pressure inside the manometer in terms of millimeters of mercury. Divide by 760 to convert it to atmospheres.